Hi there everybody, welcome to another Chem Complete lecture, and today we are going to finish the Basic Gas Laws lecture. So this is part 2 for the Basic Gas Law lecture series, and then we'll move on to the Ideal Gas Law, which is part of an entire series on how gases behave in chemistry. So if you have not seen or checked out part 1, the link will be in the description, so I encourage you to check it out, and part 2 is about to start right now. Okay, so if you recall from last time, the 4 factors that can affect gases are going to be pressure, volume, temperature, and the moles of gas present in a situation. So when we were looking last time, we took a look at Boyle's law, which related pressure to volume, and we saw that they had an inverse relationship when we organized it mathematically and laid it all out. So the goal now is to take a look at some of the other variables. Since we've done pressure and volume, we're going to take a look at temperature and moles in this lecture, and we are going to relate them all back to volume. Now, one of the reasons that we keep relating back to volume is, number one, volume tends to be one of the ones that can be a little more difficult to control as gases expand and contract as far as what they're going to be taking up. So temperature can kind of stay relatively the same if you're in a lab setting. You don't expect wild fluctuations in temperature necessarily. Moles of gas, if you put it into a given container and seal it off, you can kind of control that. All right, so one of the other reasons is if we can relate these variables back to volume and we put them all into a single law, then we can use volume kind of as the jumping off point and relate everything back to that in order to create one mathematical equation. Again, that will be the ideal gas law. So for temperature, we know that temperature is going to have an effect on gas behavior because we know that temperature has the ability to change the physical states of matter. So you think about solids that melt to liquids that eventually evaporate or end up transitioning into a gas phase. And that's usually based on temperature. We can certainly do it with pressure, but temperature is the most common as far as what we usually think of. Now, as far as acceptable units for temperature, because we are working in the metric system, the analysis should be done in Celsius or centigrade and Kelvin. Kelvin is the official unit, the official metric unit for temperature. And you can see what's highlighted in red here. Gas calculations exclusively use Kelvin. So you're going to need to be in a habit of changing over your Celsius to Kelvin. And the way that we do that is by adding 273.15 to any Celsius temperature. And if you wanted to convert back into Celsius, you would do the same, but it would be by subtracting. So you would take your Kelvin value, subtract 273.15 from that value, and then you end up with Celsius. All right? So next, let's take a look at temperature and see how it relates to gas behavior relative to volume. Okay, so this is going to be known as Charles's law. So we already looked at Boyle's law. Now this is going to be Charles' law. And this will relate volume and temperature. So we know that if a temperature is going to increase, then the gas molecules will move at a more rapid rate. And in turn, they're going to spread out further. And as a result, they must increase the volume that they are going to occupy as they continue to spread out. So the temperature of a gas increases, then the volume of a gas must also increase. So we would call this a direct relationship, okay, that is different than the pressure-volume relationship because that was inverse. So as one went up, the other went down. Now, when we're dealing with volume and temperature, both would go up or both would go down as one changes. All right. So here is Charles's law. You'll see it's a little different than Boyle's law, and that's because we need the direct relationship instead of the inverse. So it's going to be volume 1 over temperature 1 equals volume 2 over temperature 2, where the 1s represent the initial settings and the 2s represent the final temperature and volume. And again, you'll see a note, this was similar to last time when we looked at Boyle's law, that pressure and moles of gas will remain constant. So last time it was temperature and moles of gas remaining constant. Now we're going to hold the pressure and the moles of gas constant as we manipulate volume and temperature and see how they behave together. Okay, so time for practice. Make sure you've got your calculator, make sure you've got something to write with, and we're going to take a look at two examples here, and then we'll take a look at how to relate moles to volume. So, practice problem number 1 for Charles's law. A sample gas has a volume of 2.80 liters at an unknown temperature. When the sample is cooled in ice water at 0.00 degrees Celsius, its volume decreases to 2.57 liters. What was the initial temperature for this gas sample? All right, so as usual, try to identify V1, T1, V2, and T2. So take a minute and see if you can figure out which values go with which and the one that you're solving for. Pause the video and then unpause it when you're ready. Okay, so this is what you hopefully should have come up with. V1, the initial volume, was 2.80 liters. T1, that's what we need to solve for. We need to find that initial temperature reading for the gas before it underwent the change. And then, when it's cooled, V2 turns out to be 2.57 liters, and T2, with its conversion to Kelvin, would be exactly the conversion unit itself because it was 0, so it would be 273.15 Kelvin. Okay, now pause the video again and attempt to work through these by putting them into Charles' law and solving for T1. So, as usual, pause the video, unpause it, see if you were able to do it. Okay, so here we go. If we take a look, V1 was 2.80 liters, and T1 is what we'd like to solve for. And then we plug in V2 and T2 over on the other side. So first thing, let's go ahead and solve for the right-hand side of the equation because we already have all the units we need there, and we get 0.00941 liters per Kelvin. Okay? Then the next thing we need to do is try to isolate T1. Now there's a couple ways you could do this because T1 is in a denominator, so you could multiply through by T1, put it on the other side, and then you could divide through by the 0.00941 on the other side, or you can divide through by the 2.80 initially, and that will give you 1 over T1, or the inverse of temperature 1, and that's what I did here. So what I'm going to do, starting from this second line, is divide each side by 2.80 liters, and you can see I've rearranged that, but what I end up with, if I divide through, is 1 over T1. So in order to fix that and get T1, because I'm not looking for 1 over T1, I need to take the inverse of this, which is raising it to the -1. And when I take the inverse of 1 over T1 and the value it's set equal to, what I end up with is T1 equaling 298 Kelvin. All right, so put these values into your calculator and see if you can make sense of them. All right, practice problem number 2. A 48.3 milliliter sample of a gas in a cylinder is warmed from 22 degrees Celsius to 87 degrees Celsius. What is its volume at the final temperature? All right, so again, try to figure out what each of the individual variables are and then move forward to solving using Charles's law. So here's your variables, 48.3 milliliters for V1. T1 would be 295.15 Kelvin after the conversion. V2 is what we need to solve for, and T2 would be 87 plus 273.15 to give 360.15 for the total. So here's how you would solve this. You take V1 and divide by T1, V2 and divide by T2. So the left-hand side has all of the variables with values, and we can go ahead and condense that down to get milliliters per Kelvin. And then what I would need to do is simply multiply in order to get rid of the Kelvin in the denominator on the right-hand side. So I multiply through on both sides, and I successfully isolate V2. This turns out that V2 is equal to 59.1 milliliters. All right. So now we're going to take a look at moles of gas since we've looked at temperature. And for moles of gas, this will be the final variable, and it makes sense that as the number of moles of gas increase, so the actual physical particles, atoms, molecules, whatever you want to call it, increase, okay, they must push outwards as they continue to crowd up more and more. So if I put more gas molecules into a given container and I want to make sure that I continue to keep them as a gas state, then they need to spread out, because again, by definition, a gas is going to have a lot of distance between the individual molecules that are at play there. And so as they spread out, they're naturally going to need to increase their volume. All right. Now the unit for moles is simply moles, okay, but in our equations we're often going to see it represented by a lowercase n, and that will mean moles whenever we see that variable being represented. Okay, so let's take a look at this with volume. This is going to be Avogadro's law, similar of Avogadro's number. So a mole of gas will increase the room needed between the gas particles. In turn, the molecules spread out further, and as a result, they increase the volume that they must occupy. Okay, so we can see an example here with some balloons, right? As we continue to add more of whatever type of gas is here, maybe it's air, maybe it's carbon dioxide, right? The balloon must expand to accommodate that additional amount. So here is the law. This is going to be directly proportional. The volume is going to need to go up as the number of moles go up. So this is very similar to what we saw with Charles's law, except T1 is swapped out for N1, and same thing with T2 and N2. So as usual, the 1s will be the initial states, the 2s will be the final states, and we are going to hold pressure and temperature constant in this case because we're only interested in looking at how volume and moles correlate to one another. So, practice problem 1 for Avogadro's law. An athlete in a study has a lung volume measured at 6.15 liters during a deep inhalation. The researcher crew determines the lungs contain 0.254 moles of air. During exhalation, the athlete's lung volume decreases to 2.55 liters. How many moles of air remain in the athlete's lungs after exhaling? So find your variables, then apply them to Avogadro's law. All right, here are the variables. V1 was 6.15 liters, N1 was 0.254 moles, V2 was 2.55 liters, and N2, the final volume of moles, is what we need to figure out. So applying this forward, you can see it filled in each of the correct spots. The left-hand side of the equation condenses down to give 24.2 liters per mole. Then I need to divide through by 2.55 liters to get rid of it on the right side. So if I do that, it will give me 1 over the final moles. And so again, similar to the example we saw with Charles' law, I need to take the inverse of N2 and the inverse of that value. And when I do so, I end up with N2 equaling 0.105 moles. And if I double check myself, that makes sense because the volume went from 6.15 to 2.55, which meant it decreased. If the volume decreases, the number of moles should decrease. I have 0.105 compared to 0.254. So that checks out from a logical perspective. Okay, Avogadro's law practice problem number 2. A balloon contains 0.158 moles of gas and a volume of 2.46 liters. If an additional 0.113 moles of gas is added to the balloon, what is the final volume? So here are your variables. V1 is 2.46 liters, N1 is 0.158 moles, V2 needs to be solved, N2 is going to be, and you have to pay attention here, 0.113 moles plus 0.158 moles. So this is a combination of the two in order to determine what N2 is. And you needed to be careful in that step and not just grab one of those two values there. Okay? So if I put this together, here are the variables put into their proper places. And what I see is on the left-hand side, I can do the calculation. I get 15.6 liters per mole. And on the right-hand side, I need to multiply each side by 0.271 moles to get rid of the denominator and isolate V2. When I do so, V2 turns out to be 4.23 liters. And again, if I take a look at that, It makes sense because the moles were lower initially and then they increased to 0.271. So therefore, V2 should also increase compared to V1, and it does. All right, so what's coming up next? Those are the simple gas laws. We have Boyle's law, and again, go to the description if you missed part 1 of this lecture. We have Charles's law, and we have Avogadro's law. So next up, we're going to start learning how to combine some of these laws into what's actually known as the combined gas law. And then, when we combine all of the gas laws together and mix that with Avogadro's law, it will result in the ideal gas law. Now, the ideal gas law is going to use all 4 variables at one time. So instead of holding 2 of them constant, we are allowed to change and manipulate all 4. But what we're going to need in order to do that is a constant that we can set the 4 variables to under standard conditions. And this will be known as the gas constant. So we'll take a look at how that's derived and how we actually obtain the value for it. And then finally, the goal in the end of the next lecture will be to introduce the ideal gas law, and we will end up applying it to some examples. All right, so that is what we are going to have in part 3 of this lecture course. I hope everybody found this useful. As usual, hit the like button in order to help us with the algorithms so we can continue to make high quality content for you and teach you. Subscriptions will always allow you to stay up to date, especially if you click the little bell. And as always, I welcome comments and I'll be happy to get back to them. So, chemcomplete.com, go check us out. You can support us over there. We've got free resources. We also have guides for sale, pretty cheap, if you'd like to help support the channel and all the work that we're doing. I am also available for help if you need help with lab reports. I can help you with writing proper lab reports. I can also help with preparing you for tests or anything else you might have questions with. That's it, everybody. I will see you in the next one.